Okay. Today is about a brand new concept. I'm very excited to teach you about this one. This one will be a fun set of slides, I think. It'll take us a few lectures to get through them, but we're going to learn how to make our own functions. Isn't that exciting? All right, so yeah, a lot of things that we're going to learn for this lecture, but let's get right on into it, shall we? So you probably are thinking this. Maybe I've been writing all this code, right? It's all been inside of main, and main is getting pretty huge right now, right? Int main, parenthesis, parenthesis. You got your return 0 way down here. And then you wrote all this code, millions of lines, right? Maybe you've noticed like, this thing I'm doing here, I'm also doing it here. I don't really want to see this anymore. I would like this to be out of my view if possible. This is just getting a lot. It's getting to be a lot to reason about. So a very nice thing that we're going to do now is make our own functions so that we don't have to put everything in main, and we can separate all these different logical things into little chunks. So let's make our own functions where, like, we have main, and main is tiny now, because main can just call some function f1 that we wrote, and then f1 can do its thing using the help from functions f2 and f3, which is beautiful. And then maybe f3 needs some extra help still, and it can call f4. But we can write all of these ourselves. That's the beauty of functions, okay? So that's where we're going. Please yell at me if it stops making sense. Because, though, you already know how to make functions. You've been making a function this whole time. It's called main, right? We've gotten it to be extra fancy. We've added those argc and argv and things. But this is all what we know. So let's talk about what it means to define a function, because we've been defining a function this whole time. So the first thing, on the first line when you're making a function, you give what's called the return type. This will be, I'll label these. This is 1. This is the return type, int. Main returns an int, okay? We'll get to that in this bullet. Then you have the name of the function that you're defining. That's 2. That is main right here. It's the name of the function. It's called main. It's got to be there for every program that we write, but we can make other functions with different names. And then you can give what are called parameters, function parameters. They don't have to exist, but if you need them, they can go here. Remember that we made main without these for a while. You don't need them, but if you do, you can put them here. They're called parameters. And then, just like an if statement, you give the body in between braces. You give the body of the function, what you want to have happen when the function is run. That's 4. And then finally, if your function does return something, like an int, you got to give that thing back eventually with this return statement. That's number 5. And notice how the types match up. This is 0. 0 is an int. Exactly what I said I was going to do. I was going to give back an int. Here I am doing that. Okay? So, any questions about these terms, this labeling? It's not too bad, right? We've been doing this. We can use this pattern to make our own functions, though. So let's make our own function called add. Okay, very simple. It's just going to add 2 numbers. But this is how we're going to define it. We're going to say int add, and we're going to take 2 things, the 2 things that we would like to add. And in between curly braces, we'll add them. Right? And then we're going to give back their sum. So we're going to call it like this. We're going to ask for, hey, add a and b, where a and b could be anything. And then we're essentially telling C++ to go and run the function. This will make more sense when I give the example. Essentially, when you call a function, it's saying, hey, C++, go run the function's body. Run the body of the add function. Function with x set to a, because that's the names of these parameters. X is up here, y is up here. With x set to a and b. Okay, so this will make sense when I give my example, but that is my plan. So let's make an add function. All right. So we are lecture 11, I hope. I'll call this functions.cpp. I'll write a bunch of functions in this file. So yeah, here's how I want to use add. I'll be like cout add 4, 5. The whole beauty of making a function is I can call it multiple times. Let's add 1 to 7 or something. I don't know. We can do that. So let's define this function. All right, ready? So it's called add, right? What does it give back? Let's go back to this slide. It gives back an integer because I'm trying to add 2 integers, right? Int add, int x, int y. So return type, the name of the function, the things that it takes. I want to take 2 things and add them, so I'll give them names, int x and int y, like I'm declaring them. And then in between braces, I give the body, where I need to give back, that is return, the sum of x and y, whatever they are. Okay? So I need to give back an int. I need to return it. The thing I want to give back is the result of adding. That's the name I gave to this function. So let's return adding x and y. Okay? So that line, this return x plus y line, gives back the answer, gives back that sum to whoever called me. That'll make sense in the context of functions calling other functions, but this is it. We made an add function. When I call add with 4 and 5, now hopefully this writing makes sense. We're going to jump up here. We're going to jump up here, execute the body where x is set to 4. That was the thing in the first position, right? Y is set to 5. Now we're off to the races. And then x is 4, y is 5. We add those together. We make 9. We give back 9. And this will end up printing 9. Just like this will end up printing 8. Right? X gets 1, y gets 7. So let's run it. Oh yeah, 9 and 8. Does that make sense? Jump up here, run the code with these variables. These are called parameters. Set to these values, whatever we gave. And you can call this add function a million times if you want. It'll always do the right thing for the stuff that you gave. Are we happy with that? Can I increase the difficulty? All right. You might also want to have an add function for doubles. Add 2 doubles. Add 2 strings. All you need to change is these types up here. You can make a bunch of add functions with different types involved. So let's do that. You'd have multiple functions in C++ with the same name. So let's make an add function for doubles. Double add. Takes 2 doubles and adds them together. Double x, double y. They don't have to be x and y, by the way. They could be a and b. As long as you're consistent. I'll say a and b here. They're just variable names called parameters. So now I can call I can see out adding 3414 to 5.67. And this will notice that, oh, you gave me some doubles. I'm not going to call this one. I'm going to call this one. Double A, double B, I'll give back a double answer. Same function name, though, which is kind of confusing. Get my 8.81, apparently. Do we still go with that? All right. Let's do one more. Let's add strings together, right? So, I don't know. String S1 equals hi space. String S2 equals mom. I better include the string library. I'll do that in a second. Oops. I can add S1 and S2, right? If I made a function that adds strings, gives back the resulting string. So let's do that. Working on strings now. Return A plus B. So give back that answer. So now when I call it on strings, it'll go and jump up here. Set A equal to hi. Set B equal to mom. Run the body. Give back the answer. Hi space mom. Exclamation point. Yeah? Any questions about that? Are we good with that? We made 3 functions. Printing the right stuff. Okay, well, I lost my start menu, but we can go back this way. Let's do a different thing now. Let's have a different idea. Let's write a function that just prints something. We'll make a function that prints hello to the screen, maybe a new line, and this will be how we start it. Because we want to call it like this. This will make sense in a second. So I want to write a function that when I call it, it just prints hello to the screen. So I say print hello, parenthesis, parenthesis. It needs nothing. It knows to print hello. And we don't use its results or anything, so there's nothing for it to give back. It just goes off and it does something. It goes off and prints hello. Okay? That's a bit of a difference to these add functions. So let's define that one. Print hello. Well, its name is print hello. Print hello. It takes nothing, and we say cout hello new line or something like that. But what's the return type? We don't return anything here. It just does something. There's a special type for that, a special anti-type or something. It's called void. Void is when you have nothing to give back. You just want to go off and do something. You don't need the results of your computation. Your function just does something. Okay? So we'll say print hello, and it has the type void. It gives back nothing. It's like emptiness, right? The void. That's the correct return type, because you need one always, even when it doesn't really have one. So now when we call it, it'll print hello. Isn't that beautiful? And again, the beauty of functions is you write some code once up here, and you can run it as many times as you want. So I can call print hello a million times. In a loop if I wanted to. I can call it 3 times. It'll always jump up to the start, to its body, right? Start running its code, running its body. Its single line, print hello. Once, twice, and then a 3rd time. Okay, so I have 3 hellos down here now. Are we good with that? Please yell at me if it stops making sense. But we seem to be happy so far. So that is making functions. Oh yeah, question, what's up?
About the print hello.
Okay, do you understand the add function?
The add function.
Yeah, so we jump up here with these values and we just start running this code. We give back a value, right? So every time we call a function, we jump up to its definition, to its body, and start running it. So when we call print hello, we don't give anything, but we jump up to it and we start running its code. That one line, it gets run. Does that make sense? Yeah. And so we jump up here 3 times if I call it 3 times. And it knows how to go back to, all right, once this one's done, it knows to go back to this line 36. And then when I call this one, it knows to go back to line 37 once it's done. And then once this final one prints its hello, it knows to go back to line 39. That's the last thing to do in main. We'll talk about that later. Yeah, that was a good question. Any other questions? Okay, so we know how to make functions. Now let's go back to this. I gave you this slide way back in the beginning when we were talking about library functions. Now we can explain it further. All right, so when you call a function, you have to, of course, say its name, right? You're shouting out to it. So that's 1. When you call a function, you have to supply arguments to, right? That's these. They're called arguments. And when the function gives back something, optionally, if it does give back something, if it's not void, you can get that C, right? You can get the result. Put it somewhere. Or just immediately use it, all right? So remember that up here, these variables involved in a function definition, they're called parameters. Those are the things that it's using to do to compute its answer. When you're calling the function, the things that you give are called arguments, right? So the parameters in the definition get the arguments when you called it. So let me like copy and paste the declaration of the add function. Add int x, int y. Now we've finally come full circle. And then it starts being defined, right? When we call the add function, we put the a up in here for x. We start running the code and we set x to a. We start running the code and we set y to b. And now x and y are what we think they are. And it starts adding those things that we originally gave. So the parameters in the definition, they get the arguments in the call. Okay, that's just a terminology thing. I mess up those terms all the time. Call me out, please. So this is like, I don't know, diagram 4. Okay, so you got your function definitions, all this cool stuff, function use, function calls. Now I have a question for you. So here are two functions. You got a main function and a 5 function. And look at what main is doing. It's like see out 5 times 2. Harmless, right? There's something wrong with this code. All right? And so I want you to get into peer instruction groups, say hi, and see if you can put your answer in the Google Doc, if you're confident enough. So go to the written ice page. I'll clear it out. And then let's see what we're thinking. Because there is an issue here. Can you spot it? Why is it not as cool as our add function or our print hello function? What's going on here? Try your best not to code it up, but if you'd like to, you can. I'll give you like, I don't know, 3 minutes to discuss. And please ask me if you have any questions about it. Let's see if you can write down and notice the problem. There's something wrong with this code. What? Oh, nice, yep. Bonus points if you write down how to fix it. Subtle, right? It's okay if you can't notice it. Take another 30 seconds or so. Write down your good ideas. All right, that's my timer. Did we notice it? Let's see. What we got? Calling cout 5, but then the cout statement is acting like it's an int when it's actually a cout statement. Yeah, so cout is just printing to the screen. It's not really giving anybody the number 5. There's no return statement. Good. That's another issue. That's maybe the main issue. Doesn't return anything, so you can't multiply the return value as you would expect by 2 because you have nothing to return, right? Good, somebody fixed it. Nice job, Group 20. Not returning an int. You can change the return type. Yep. Very nice. So the groups who noticed it, good job.
Do the survey now?
What job?
You want me to do the survey now? My wife's
Oh, okay. Okay, in that case, yeah, go for it. You need me out of the room or something?
Yeah, I mean.
Sure. Let me pause the recording. Okay. Slowly learning how to use this. All right, so let me code this up and let's see if it even compiles, right? I'll call it ice.cpp. And I guess I gave it a main function. Let's do this. Oh man, PowerPoint. It puts weird characters that aren't spaces. Well, let's go to all the, oh come on. I'll just type it out, never mind. Void 5, cout 5, and then silly. Give me main function. Then we're going to call it. And multiply its result by 2. That is the same, right? Looks like it. Okay. G++ ice.cpp -o ice. G++ is so useful. Look at it. It's like, all right, invalid operands of types void and int to binary operator star. It's like, you gave me an int over here, you gave me a nothing over here. I can't multiply nothing by a number. What are you talking about? So this won't even compile. Okay? That's lovely. How do we fix it? We have to give back a value. Okay? That's the idea. So this function right here, if this were to compile and run, it would be like on the terminal, it would call this function. It's like cout 5 times 2, so it has to get this result if it gives 1 back. So it goes and it runs 5 first, which prints 5, gives nothing back, and then it tries to multiply the nothing by 2, and who knows what it's going to put here. So it would first print 5, and then maybe some other answer if there was one. Okay? So this is a function that just prints 5. And it's not the same as a function that gives back 5, right? The answer would have been to be like int 5. A function that gives back 5 and you return to give something back. Okay? Those are not the same function. This is the one that it should have been. If you actually wanted it to give back 5 here and then make 10 and print 10. That's the one we needed. Okay? Any questions about that? So I have a whole other slide on this. This is such a common error in this class. I just want to show you it right now because you will make this error, I promise. But at least now you'll know how to fix it once you notice it. Okay? So this is the age-old issue of returning versus printing, right? And to make it clear, to see how you can do stuff, I like to think of it as, you give me this function, how can I use it in main? You give me this function, how can I use it in main? Okay? So a function that gives something back, for example, I can say add 3, 4. That gives back the answer, right? That gives back the answer of 7. I can pretend I have 7 here. And then I can add it to 2 or something. I get to imagine that each call gets replaced with its return value. So this becomes 7, essentially. And I can save that into some other integer, into C or something like that. That's all possible when I give something back. Every call gets replaced with its return value if there is one. Okay, so I can do this. Add 3, 4 is going to get replaced with 7. I can say cout add 5, 6. That's going to get replaced with 11, and it will end up printing, right? Assuming we implemented add properly. Okay, that's how we can use those in main. This function is very different. A void function just gets to be called on a line by itself. You cannot use it in a larger expression. Print hello, parenthesis, parenthesis, semicolon. That's all you get to do for a void function. You can just call it on a line by itself. You cannot pretend that it gives something back. You can't be like, see out the result of print hello. So it's like it prints hello when it gets called, and then it also gives something back to then be printed by see out again. That makes no sense. This gets replaced with nothingness, because it gives back nothing. So assume that each call to a function that returns something gets replaced with its return value. All right? So I hope that makes a little bit more sense. So, yeah. Let me show you both ways. Let's take this code, return versus print.cpp. Let's steal our functions.cpp file, and we'll just take the ones we care about. Let's take just the first add, and then we'll take the print hello. Okay. So here's how I meant to be using all these. There. I can call add45, it gets returned, that 9 gets returned and it gets printed out. And I can call print hello, and it goes and jumps up here and prints hello. So let's compile and run that. Return versus print. So that works. What I can't do is be like, see out the results of print hello, right? Because it gives nothing back. That makes no sense. Won't even compile. Oops. Go back. Oh gosh. There we are. Won't even compile. And this is extra horrible of an error message, but let's see. If we scroll up to the tippy top, it's just saying, I know how to print out all these things. You gave me something that I don't know how to print out. It's like, I'm trying to print void, to print nothingness. I have no way of doing that. So that was its error there. And so it won't even compile. Oops. There. Okay. So this won't compile. Also, it makes no sense to do this for add 4, 5. Why not? Why couldn't I just do this? What's wrong with doing that? It's going to compile. It's going to run. What's the point of running this? It's going to compute 9. What does it do with 9? It gives back 9. Do we use that value? It does nothing at all with that value that it took so long to compute, right? So just like it makes no sense to print the result of a void function, it makes no sense to call a function that returns something on a line by itself. Food for thought. Any questions about that? That's some new concepts, that's for sure. So those are the two sides of that coin. All right, we good to keep going? All right, so now that we've made functions, the whole point of a function is to make it so that you can have a nice piece of code that you can put somewhere and call multiple times, that maybe can itself call other functions. It helps us solve problems in a way that we as humans can like come up with the answer to, right? We can send off the problem down to somebody else, and eventually we'll get down to a low enough level where we can just write functions that make sense to us, rather than just doing everything in main. Right? So let's talk about how to break down a problem, because this is going to be essentially your life as a computer scientist. So let's say your boss comes to you and they're like, hey, I need you to sum the squares of all the numbers from 1 to n. Okay? So you need to ask yourself, how in the world can I do that? Because that is what you're apparently getting paid to do. So for example, say if n is 3, then you need to compute and sum together 1 squared plus 2 squared plus 3 squared. Okay? which is 1 plus 4 plus 9 equals 14. Okay, so that's the game. And this is a problem, all right? So let's break it down and let's solve it using a bunch of different functions, all right? Because that is how we solve problems in computer science. We make up our own little algorithms, all right? And let me give you a nice little way of trying to come up with those algorithms, okay? Nice little method that usually works. So if you're having trouble starting, this should help, all right? So remember what an algorithm is. It's just a sequence of steps. It's a recipe to end up with something that you care about, okay? It's like, you give me this, I will then produce that. Then I'll go off and do this, and then depending on something, I'll either do this one or this one, but in the end, I'll still get what you wanted. Like that, that's an algorithm, right? Maybe a loop is involved. So yeah, the goal of this class, now we're ready to start learning it, now that we know enough syntax, it's learn how to break down a big problem into little pieces that you can then go and solve, okay? So make a bunch of little tiny algorithms. We're ready to do that. And eventually, those little tiny algorithms are going to make so much sense to you that they're immediately solvable. You can write those functions in the blink of an eye, and then everything just comes together towards the end, okay? What I have been giving you is step-by-step instructions on how to write a program, right? That's what I'm going to start not doing. I need to get you to stop doing that. I want to get you to think by yourself from now on. Okay. So essentially, to program, here's what you do. You read your problem, you figure out what it's trying to do. There's always a concept of the input, right? So the user is asking for n, right? They're telling you what number to go up to. That's like input to your algorithm. You figure out what the input is, and then you go off and implement it, right? We'll also talk about how to make sure that we did it right, how to be confident that we did our program and it worked properly, how to test our code, how to debug our code until it is correct, all right? And then finally, something that you already know how to do, when things start going wrong and you're trying to figure out like what is happening in my program at this point in time, even the greatest programmers use cout still. They just print, okay, what are the values of these variables right here on this line? Let's see how they change. That is a valid debugging method, and it will stay with you for the rest of your career, okay? So yeah, let's solve this problem in a nice cookie cutter broken down way, all right? So here is the problem. Let's find the pieces, right? What are the different pieces of this problem? Can I break it down into little pieces? I think so. So one piece is I need to sum a bunch of stuff, right? I could just work with that. If I knew how to sum a bunch of stuff, I can give the things that I need to sum and get back the answer, right? So that's one piece. I also need to be able to square numbers, right? If I knew how to do that, that would make my life easier. And then finally, I need to start, right, with the numbers 1 through n so that I can bring them through that process of squaring them, summing them, all that kind of stuff. So those are the 3 different pieces that I see. Does that make sense to us? You see how I broke that down? Those are the 3 pieces of this problem. And they're all kind of independent from one another. Next, we want to track the flow of data, right? So what needs to happen before something else? I need to sum the squares of these numbers, so I better start with the numbers, right? This is number 1. I need those numbers first, because otherwise there's nothing to square or sum, right? I need these first. Then I can give these off to the squaring part of my algorithm, right? Because then they can be squared. That's step 2. Then I can give those squares of those numbers off to sum. And then I sum them together, right? That could be step 3. That's the way the data is going to flow in my program. Does that make sense? That's how I broke down the problem. I noticed who needs what, that kind of thing, what must be done before what. That's all programming is, breaking it down like that. And now that we have functions, we can just make a function that sums, a function that squares, a function that enumerates these numbers. Those all make sense separately, and we know how to hook them up together. We have the answer, right? That's how we think as a computer scientist. Okay, so let's get started. Let's do this. My recommendation for you when you come to like a large problem that you're faced with you get all these ideas, all these little pieces, you know the functions that you're going to write, and then you start them off with silly implementations. Okay? You start them off with silly implementations that are called stubs. All right, so let's talk about that. Let us begin. How do I want to do it? Let's just start writing some of this stuff, and then I'll talk about it. So, sum of squares. We're trying to solve that problem. Not CBP. So let's say the user is going to give us the number, right? We'll be like cout, enter n, because that was part of the problem definition, right? It's like sum all the squares from 1 to n. So that'll be part of our problem. So we'll get that. And then we'll be like, all right, well, wishful thinking, right? I'll just call my sum squares from 1 to function with n as the parameter, as the argument. If I had that, the problem's solved, right? Not sum squares from 1 to n. And that's how we can keep going, all right? So what does this function need? Well, it needs to give back a value. It needs a number n. And that's pretty much it, right? It's got to enumerate stuff. It's got to give back values. It's going to then go and call some functions. It's going to call a square function, right? A square function that takes a number and gives back its square. Then we're also going to need to call a sum function, right? I think we'll need to do that too. But that should do it. We can bring in our add function. That can be our sum functionality. Not that we needed it. But here's what a stub is. It's like, all right, I know that I need these functions. I'm not really sure how to implement them yet. Let's just get something compiling. Because right now it's not going to compile, or it's going to warn me. It's like, this function needs to return an int. Just be like, all right, return 42. Return 42. Is it going to be correct? No. But at least you can get everything hooked up in the proper way. You can see, like, is this going to compile now if I just gave the implementations? That's what a stub is. Boop. So enter n, 500. The answer is, of course, 42 right now, because that's what it's giving back. So that's not correct, but it's called a stub. It gets us started. Right? It's a function that gives back a dummy answer. Just make sure you give back some value of the proper return type, and then you can just make sure everything is in the right place. Right? And then you can go off and implement it. Right? So now we're ready to actually write the function. Functions, plural, I guess. So what do we need for sum of squares from 1 to? We need to start with these numbers, right? Which means we need to enumerate them. We need to loop, right? We need to loop through 1 through n. And every time we have a new number, right, we better square that number, right, with our square function. Every time we have a number that we get back from square, we need to add it into some final answer variable that holds the total sum. So I can use the sum function. I can use the add function for that, just for fun. Could have used plus, but let's get enough practice with using functions. So here's the idea. Sum squares from 1 to. I'll start a sum variable off, and I'll enumerate my values from 1 to n. For int I equals 1, I is less than or equal to n, I plus plus. Because I needed those first, right? I need to enumerate my numbers from 1 to n, because then I could square them. And then I could add them into my sum. Okay? So, well, int I squared is, well, let's call square of I. Now I have that number squared, and I want to sum those all together, so I better add them into my sum variable. In a silly way, we'll just say sum equals add sum and square. Like I forgot what plus was, but we're just using extra functions, okay? That's the idea. Okay. Do I have add still? What is it unhappy about? I'm not sure yet. We'll figure it out together. But that's kind of the idea. So we're going to add up all those numbers into sum. And then finally, once this for loop is complete, I've squared every number. I've summed them all into the final sum variable. I have an answer. The answer is whatever is in the sum variable. Does that make sense? That's the beauty of it. Oh, sorry, not sum square. It's I squared, that variable. Okay? So I'm enumerating all the numbers. I'm squaring them. Boop. I'm adding them into my sum. Step 3. Does that make sense? Still not quite correct. Add is fine, but square is still a stub. It thinks any number squared is 42. How do you square a number x? You give back that number times itself. Yeah. So those are the implementations of all those functions, and here's me using them down here in main, calling my sum squares from 1, 2 function. And it's going to do it right. What was the number that I gave first? It was 3, right? And the answer is 14. The 1 plus 4 plus 9, that is 14. Sum squares of all the numbers from 1 to 100 is apparently that. Are there any questions about this? Oh, sorry, I didn't show you the edge of this final function, the bigger function. Add, we know. Square was new. The sum function was new. Sum squares from 1, 2 function was new. Okay? Are you good with that? That's pretty neat. Alrighty then. And if we're happy with that, let me show you another cool thing that you can do now. Because main is usually what somebody who looks at your program wants to see. Let's make main first. That was this. You can declare, just like you can declare a variable, you can declare a function. You can declare that it exists. I promise to write a foo function that takes an int, and then you can put a semicolon instead of a body, and then later on you can define the foo function. Isn't that cool? So that's usually what you're supposed to do. You declare them up before main, and then main is like the star of the show. It's the first real function implementation, and then all the other stuff that main is using is defined below it. Okay, so you can declare a function, just like you can declare that a variable exists. So this is a function decl. This is a function impl. That's enough. Okay. So let's change these around now. Let's put all these below main. And now it won't compile right now, because it's like, I don't know what sum of squares from 1, 2 is. It's like, it's got to be in order for C++. So let's just say that it exists.
For example, you're showing like int add x plus y. It has nothing to do in this function, right? Or it's just like there.
I'm using add right here.
Oh, okay.
Is that what you're asking?
Yeah.
Yeah, it wasn't for nothing. I could have just used plus, but I wanted to use our add function that we worked so hard on. So you can declare that all these functions exist up here, and then you can define them below inside of main. Okay, so these are the function declarations. That just promises, like, eventually I'm going to write a function that looks like this. I promise to give you a function like this so that you can actually jump to the body now. But that's one nice way of writing your code. Declare your functions up before main, then main is the star of the show. It's the first function really there, and then you've got all your implementations below. Okay? No real difference. It's the same program, still compiles, still runs. It's just a little cleaner, I guess. Usually why people do it. I'm going to teach you style as well as syntax. All right. Are we good with all that? That was just breaking down a problem, an example of something that you will be doing for forever from now on. All right. Let's move on then to testing. Testing will allow us to be confident in our programs and believe that they actually worked. Okay? So I am testing your programs right now when you turn them in, but I want to teach you how to test your own programs. So how do you know when your function is correct for some definition of correct? it'd be really nice to know that it's always going to work, like just prove once and for all that it's going to always do the right thing no matter what input you give it to it. Sometimes it's possible, like if you have a function that takes a bool, you can be like, all right, let's run it for the parameter being true and the parameter being false, and let's see if those were what they were supposed to be. If so, it's a correct function. It gets a little unwieldy, though, when you have like int parameters. There's only, though, about 4 billion ints. If you'd like to run your program by hand typing each int in and looking at the answer and confirming that it's correct, that would still work. If you tried them all, you could be 100% confident that your function that took an int was correct if you tried all 4 billion of them. But that's not very feasible, right? So, though there are ways to prove your function's correct once and for all without trying every single one of them, there's a lot of math involved in that. You can have to wait until CSCI 26 to get into that cool stuff. Right now, what we can do is we can use the most common thing that people do, and we'll just write a bunch of tests for our function. Okay? With more tests that test different kinds of things, edge cases and things like that, we will be pretty confident that our code is probably perfect. Okay? So we'll write a bunch of things called unit tests. So yeah, what is unit testing, you might ask? That's when you take a small piece of your program, usually just a function, and you write a bunch of test cases for that little chunk. So that's what I'm doing for your code when you submit it to the autograder. Okay? So, to make it simple, let's have a concrete example of testing. Let's have a factorial function. All right, so let's write a factorial function that gives back, like you ask it for the factorial of 5, it will give back 5 factorial, which is equal to 5 times 4 times 3 times 2 times 1, right? That's what a factorial is, that exclamation point thing. So let's have it take an integer. What's the return type of this factorial function? What should it be? What kind of thing does it give back if I ask for the factorial of 5? Does it give back a string?
Integers.
Yeah, I'm multiplying a bunch of whole numbers together, so the result can be an int. That's fine. Are there any parameters? Can I call a factorial just by itself without anything, and it always gives me back the factorial of 5 or 6? Can it read my mind? No, I needed to give it a parameter, a single parameter, the thing that I want to take the factorial of, and it is an int, right? Factorial of 5. Mathematicians have defined what it means to be the factorial of like 4.5, but we're not going to go there. The name, we can just call it factorial or facts or something. What did I call it before? I just spelled it out, factorial. And with all this information, we can start it off. So let's write a stub for our factorial function. All right? So this will be testing.cpp. I think that's what I want to call it, yeah. Testing.cpp. So, I don't know. How do we want to do this? Here's a factorial function. It returns an int. It's called factorial. It takes a number that we want to calculate the factorial of. Let's call that n. And if it's a stub, let's just say it always returns, I don't know, 42. That's the factorial of everything. It's always 42 right now. So that's fine. That's an incorrect implementation, but at least it's going to compile right now. All right? So that's our factorial function. And now, even before we start writing its body, let's write a bunch of test cases. All right? A test case is a Boolean expression. Do you remember what that means? It's just a fancy word for something in C++ that gives back true or false, something that results in true or false. Something that results in true or false. And the test case is this, and it compares what you expect when you call the function. Like I called the factorial of 3, that better give me back 3 times 2 times 1, which is equal to 6, with what you actually got. Like you actually run the function, see what it gave back, maybe it gave back 42. You compare that with the 6 that you should have got, right? That is the goal. All right, so let's write one test case using an if statement. Here's a test case. If the factorial of 3 is really equal to 6, it gave back the right answer, right? Then it passed the test. I don't know. we'll say passed, all caps, factorial of 3. Otherwise, we'll say failed. Factorial of 3. That's a test case. This will get replaced with what we actually are giving back in the function, and this is what we expected to see, right? That would have been the right answer. That's a single test case called a unit test. And of course, right now it's going to fail because it's giving back 42, right? So our function is not yet complete. It's not yet correct. That is a test case. Okay, so normally we don't write our test cases like this because, like, if you wrote another test case, it'd be like, if the factorial of 4 is equal to 24, right? Then it passed. Otherwise, it failed. This gets to be repetitive. We can put that into a function, and the function is called assert true. So it's a void function, void assert true, and it takes a Boolean as its first parameter, and then it takes a string in its second parameter. And watch what we can do. We can take this idea and generalize it. So assert true, just see if your Boolean expression was true. If B, right? If B was true, then you passed your test. And the test had some description involved in it, some string. Otherwise, we failed the test. And the test was whatever the Boolean was. We expected it to be true. We're asserting that it should be true. And we give the description. So this is like what this is. And so we can translate this now into an assert true call. So instead of this, we can say, oops, I'll try and get this on the same lines for us. Instead of all that, we can say assert true that factorial of 3 is equal to 6. That's our Boolean value. It should be true, right, if it's correct. And our description of the test is factorial of 3. Do you see how this is going to jump up here and become equivalent to this code? That's much cleaner. Any questions about that? That's what people like to use. They like to use this assert true function a lot of the time. So we don't need this, these if statements anymore. Instead, comment them out. We'll say assert true, factorial of 3 is 6. Assert true that factorial of 4 is 24. And so now I've got 2 tests that jump up here. Actually, here. Boop. Call assert true down here in main. They both fail right now, and sorry, this was supposed to say factorial of 4. That was its description. Okay? Any questions about that? Those are tests. We want a bunch of tests. The more the better. The edge cases are very important too. Like 3, 4, 5, that's plenty. It's supposed to be 24 times 5, then would be that factorial, and I think it's supposed to be 120. Let's test edge cases. The factorial of 1 should be just 1, right? And this was factorial of 5. Oops. This was factorial of 1. The factorial of 0 is actually defined to be 1 as well in math. That's fine. That can be a test case. Make sure it's 1. And then anything other than that, like the factorial of a negative number, doesn't really exist. So let's say that every time we call factorial on a negative number, it gives back just -1 as some dummy answer, just to alert the user, hey, you did this wrong. Okay, so these are a bunch of tests, and they all fail right now. If we got them passing, would you agree that our factorial function is pretty close to being correct, if not perfect? That's what tests are all about. So let's implement our factorial function. So, I don't know, we have some product that we're giving back, prod, start at 1, and let's iterate. For int I equals, start at n, I is greater than or equal to 1, I minus minus. So n times n minus 1 times n minus 2, 5 times 4 times 3 times 2, all the way to 1. Product equals itself times I, return prod. That'll work for the bigger factorials, and it'll also work for factorial of 0. But watch this. If I ask for the factorial of a negative number, it's going to give back, like it's not going to go through this, because I is going to start out at -1, and -1 is not greater than or equal to 1. It'll just return the default value of 1, which is not correct. If we get a negative value, we need to give back -1. So that still fails, but the rest pass. So let's fix that. If n is less than 0, then return -1. That's just our dummy value that we always give back if the user called us wrong. There is no factorial of a negative number. And now, every single one of these tests, even the corner cases, like this one, all these, they're all passing. And you can be pretty confident that your factorial function is correct once you get all of those tests that you made and thought hard about to pass. Does that make sense? That's what you've been doing in your labs. Now we've just brought in the idea of making your own tests. Are we good with that? Now you can make your own. So yeah, it's very important to be thorough. Just don't check like factorial 3 and 4 and 5 because they're all going to go through this loop, right? Check the corner cases. Do you cover everything? Do you try every different kind of input? Corner cases are things like, oh, inputs that don't go through this loop ever, right? Like 0. Inputs that go through this loop just once, like 1. Those make it a little more tricky, right? Those are our edge cases, 1 and 0. And then -1 is a special case that we needed to handle that we forgot about. That's very important. So the word cover is just kind of a metaphor for like you're putting a blanket on all of your code. You're making sure that everybody is accounted for. So you check your corner cases, and like you make sure that if you have an if-else statement, you have one input that goes through the if statement's body, you have one input that goes through the else case's body. You want to try both, make sure that both of them are going to do the right thing. If-else statement body is etc, right? So we have one input that hits this if statement's body, this one. We have a bunch of other inputs that don't hit that if statement's body and do the rest of the work, okay? So that is how to write your own tests. You want to cover your code. Make sure that everything is accounted for, every different way that your program could have executed when it ran that function. You have a test case for that, okay? Because then you can be pretty confident that it's working. Any questions about that? Are you happy with it? All right, because the last things that I want to do today are questions for you. So let me give you the assert true function. Oops, is it going to let me give it to you? This is just all you need. You need the first line to know how to call it, right? So here it is. Boop. It takes a Boolean and a description of what you're trying to do. There you go. I'm also going to give you this question, but here's the first one. So here's a square function. I claim that there is something very, very wrong with it. So see if you can, 1, discover the error, 2, write a test case using assert true that's going to fail. That will discover the error. That will exhibit the issue. Okay? Does that make sense? So discover the error and write a test case that will eventually pass if they fixed it, but fails right now. All right? So I'll give you maybe 2 minutes to try this. So please help each other. See if you can figure out what to do. What test case would discover the error and fail? Though it should have passed if it were correct. Try running the code in your mind. Is it doing what you think it would do? It's meant to square the input, right? Give back the square of the input. Input's a double this time. You don't have to write down your test case on the page or anything, just among your group. Thirty more seconds. All right. Do we see it? What's the problem with this function? What's square of 1 returning? Is that correct? So that's a bad test case to discover the error. That one's going to pass right now, right? What about square of 2? It returns 2 right now. It returns x. So that's the error, yeah? It should have been what? So that's our assert true. Assert true, square of 2 should have been, if this test case passes, it's correct, right? You always write it in that way. Square of 2 is supposed to be 4. And then you give some description, be like test 1 or something. I don't know. That's a good call. That's a good test. That's going to discover the error. It's going to fail right now, right? But it should have passed. Does that make sense? Why that is a good test case? Any other one works too, like square of 3. It's going to give back 3, but it should have been 9. It's always compare what you got back with what you expected to get back. Okay? You hard code it. That's a test case. Are we good with that? Question, yeah. My next question. So here's another good thought, though. So I'll give you 1 minute now that we heard the answer. But is this version correct? Now it's going to return squared number. Is that still okay? Write a test case. I'll give you a minute for that one. Good thought, though. That's exactly where I was going with that. What would the right test case be here? Definitely write it out. I'll give you a minute to write it out. You see how important it is to write good test cases? that really do cover the problem well. All right, so what does square of 2 return right now? It's really 2.0, right? What will that give back? 4. As a double, it's correct, right? That is a correct test. Like if you had a test for this one, like this test will now pass. We fixed it, right? That's why you need more tests. What's a good input? Yeah. Square of 2.5 right now is going to give back what? Gosh, it's going to make squared number. Squared number is an int. So this is going to get weird. It's going to compute 2.5 squared, which is apparently 6.25. It's going to compute 6.25, but then it's going to try and shove it into an int, right? Which is going to make 6. So it's going to give back 6, and there's the error. Okay? So here's your assert true call. Assert true something, I don't know, call it test 2. But I need to call my function, square, on the input, 2.5, and then what do I check it to be? It better be the right answer. Yeah, 6.25. And again, this is me sidestepping the issue of you shouldn't be checking doubles for equality. Really, what you should be doing is having some approximately equal function call here. That gives back true if it's close to 6.25, but this is good enough for us right now. It's like, this is what you got, this is what you expect. It better be the same. Okay? So that's another good test. So, yeah, I think we noticed the pattern. Like, it's always you call your function, what you got, this is what you expected. What you got, this is what you expected. And then with these tests, I think the implementer will finally get it right. Yeah? Once they get them all passing. They'll notice the error and fix it. So that is testing in a nutshell, how to make your own, how to think about which tests to create. Are we good with that? Any questions about any of this or anything else we talked about today? We came a long way. Yes? Mm-hmm. This is the name of the parameter. So when I call this function, like here, with a 3, it's going to jump up here and start running with n set to 3. It's that value that I gave when I wanted to run the function. And if I call it again with 4, it's going to jump up here and set n to be 4. I needed a variable to hold what the user gave me as an argument. Does that make sense? It's called a parameter. It could have any name. This could have been x as long as I used x in the body. It's positional. So like it's the 0th thing that's going to be filled in with the 0th thing that's given here. Just like the add function, when I call the add function, it takes 2 things. Their names don't matter, but their positions matter. The first thing that I get is going to be placed into x. The next thing that I get is going to be placed into y. Okay? Yeah, it definitely takes some practice. But that's the gist of it. Any other questions? All right, because I promised you a new lab. It won't be due this week or next week. That would be evil. But it'll be due week 8. So we are in week 6, so that's 2 weeks from now. So it'll be due on the 30th. So that's a Friday, last day of this month. Lab 4. All right. First thing, starting from this lab onwards, you are allowed to work in pairs if you would like. You can find another student in the class and work with them. Pairs of 2, though, not groups of any more than that. That's as big as they can get. What I want you to do, though, you'll share your code with each other, work on things together, but I would like you to still submit separately to the autograder your own copies, because that's just much easier for me to give you a grade that way. But please include a comment saying that you worked with somebody, because I don't want to notice identical code and think the worst, right? So just tell me that you worked with somebody, tell me who they were, somewhere in your code, okay? I can help you if you're not sure about how to transfer code among your partner, between you and your partner. There are some very cool ways of doing that. And yeah, if you'd like, post on Discord saying, hey, would anybody like to work with me? Something like that, if you're interested. If you don't want to do that, I can maybe make a list of people who want to partner but don't want to ask on Discord. So see me if you want to be added to that list or something. And then I can pair you off with people myself, if you'd like. So yeah, that is logistics. You can work in pairs now. All right, let's talk about the code. So let's connect to the server, if it'll let me. All right, so give me labo4 at CSCI 40, cd labo4. So I got these three files: longest word.cpp, shakespeare.txt, and vectoroperations.cpp. First program, calculate the longest word in a file, or in your input, okay? So the first program is going to be interesting. You are going to compile your program, and you're going to run it like this down here. You see this? / the name of the program, and then you put a less than sign, and then you put the name of another file in your directory. It's kind of weird. What that does is it redirects the file to CN. It's like the user pretends to type the entire contents of this file. And this file is a very long file. It's the entire works of Shakespeare. We'll talk about that in a second. But you are going to want to read every word from CN. Just pretend that the user is typing it, because it's going to go to CN. The file is going to go to CN when you use this less than sign. Okay? So just keep on reading words at a time. Eventually, it will have nothing left to read. So the longest word.cpp. I've given you the start. This is a weird piece of code. Okay? While CN read into current word, that's the condition? What? This is weird. But what it does is it will try to read a word into the current word variable. If it is successful in reading another word, there was another word in the file, it will run the body. So you can assume if you got to the body, there was a new word to read. Once there are no more words left in the file, or in the input, then the while will become false. This condition will become false. It turns into true or false based on its result, which is really weird. But it works out very well for us, because we can just say, while we can get a new word, process it. And then once you're done, you have read every single word in the file. Okay? So just read the comments. You'll get used to it. But that is a very nice piece of syntax. It'll become false after you've read every word. And what you're going to do is you're going to try every word in the file and find the longest one. Apparently, the longest word in the Shakespeare.txt file is this giant thing. You don't have to get rid of any punctuation or anything, but this is what you should see when you have a correct implementation. Okay? And you should test this out by making your own files. Well, remember what CN on a string does. It gets an entire word. Yeah. It's special for strings or ints. But yeah, it'll read a thing, and it'll put it in this variable. If it actually got something, it'll run the body. It was a truthy result. It's just a weird return value for the input on CN. Now you know those words. Any other questions? Because yeah, you'll use, it's kind of like a maximum question, right? You're finding the maximum length word, and then you'll print it out. Make up your own files. I gave you one. I'll be testing you on more than just one. But here's the entire works of Shakespeare, starting with his sonnets all the way down to whatever the last 124,000 lines. So the longest word is apparently this one. Make up your own examples though so that you can try it out. So that's that. Yeah, make some sample files to test your code. Calculate longest word, that's your first one. Second one, write a program to perform various vector operations. Okay, this is called vectoroperations.cpp. What you're going to do is you're going to run your program, and you're going to get command line arguments. Ooh. You can have as many as you need, maybe 0, maybe 1,000,000, and all of your command line arguments, you're going to place them into a vector of ints. Okay, so 1, 2, 3 is going to make a vector of 3 ints. It's going to keep pushing them back. And you're going to calculate all these things about the vector that the user had you create. So 1, 2, 3, you're going to calculate the minimum, the maximum, the index of the minimum in the vector, the index of the maximum in the vector. You'll also be calculating the second smallest element and the second largest element. They might be the same. If you run it like this, vector operations with some other bunch of numbers. This will be the order of the vector. So the minimum is 0, the maximum is 5. Those are the values. Then the indices, the minimum lives at index 3, 0, 1, 2, 3, right? The maximum lives at index 0, 1. And then the second smallest element is 2. The second largest element is 4. So those are the kinds of things you'll calculate after you read this vector in to read that input into a vector. That's what I'm trying to say. Okay, so you need argc and argv. You're going to take every command line argument except for the name of your program, and you're going to put them into this vector called v. All right? So you got to read all the command line arguments, convert them to ints, because they are strings to begin with, right? Put them in v, and then you got to find all the things. Find the min, find the max, the index of the min, index of the max, the second smallest element, and the second largest element. Okay? My hint for those is me including this line up at the top. Think about why I included that for you. That's my hint. Okay? So, yeah. You're going to get command line arguments, read them into a vector of ints, remember to convert, and then calculate this information about each of those things. Okay? About that vector you built up. Any questions about that? You can assume the user is always going to call it with at least one value, so there will be a minimum. There will be actually something there to be a min, a max, second biggest, second smallest, something like that. Or sorry, you can assume that there'll at least be two things, because you're going to need a second smallest and second largest thing. So it's incorrect to run the program without at least two numbers here. I'm not going to try and do anything like that to you. Okay? Guaranteed to have at least two elements in that array that the user is trying to type to you. Okay? And have you put in the vector. So I think that's everything that I wanted to say. Any last questions about this one? About the lab in general? Those are the two pieces. And you'll be submitting your CPP files, longestword.cpp and vectoroperations.cpp. Okay? And I think that's all I have for you. So that'll be due in 2 weeks on the 30th.